We've talked a bit about energetics and how a system at equilibrium is at its lowest energy state. We can actually go a bit further than that, though, when it comes to relating energy or thermodynamics and equilibrium. Energy and related terms are classified in different ways. In an earlier video, we talked about enthalpy, represented as H, and the change in enthalpy, delta H, which is also called the heat of a system, and in the world of chemistry, a system is most often just a reaction. Another important measure of energy is the Gibbs free energy and the Gibbs free energy change, as delta G. You may remember learning about delta G in previous quarters, specifically regarding spontaneity. As a refresher, if delta G is negative, the forward reaction is spontaneous, as in it goes without the need for extra energy to be put in. Likewise, if delta G is positive, the reverse reaction is spontaneous. And now for the new material. If delta G is neither positive nor negative, equal to 0, neither side of the reaction is favored. Therefore, the system is at equilibrium. We can show all of these things with one expression drawn here. And in this expression, delta G naught is the free energy change under standard conditions. So what I mean by that is room temperature, all of the pressures are 1 atmosphere, and all of the concentrations are 1 molar. R is the ideal gas constant in joules per mole Kelvin, T is the temperature in Kelvin, and Q is the free energy reaction quotient. So I should note here that Q in this case is not necessarily QC or QP, which we've learned about earlier. And as a reminder, QC is the concentrations of products of a reactants, and QP is the partial pressures of products of a reactants. Instead, Q will always use the concentrations for aqueous substances and the partial pressures of gaseous ones. So for example, in this reaction that I have drawn here, where we have CO2 gas mixing with liquid water to form aqueous H plus and aqueous HCO3 minus, the free energy reaction quotient for this reaction is drawn as such, where we have the concentrations of our aqueous products and the partial pressure of our gaseous reactant. So this is because the delta G term is standardized to 1 molar for solutions and 1 atmosphere for gases. So just remember that even though you've previously seen QC for either solutions for gases or QP just for gases, when we're using these free energy equations, we're going to instead use a combination of the two. But anyway, back to the free energy change equation. Now, delta G naught is sometimes just a known value that we take from a table or something, but we can also relate it to the free energy equilibrium constant, K. Recall that at equilibrium, delta G is equal to 0, and also Q is equal to K. So we can rewrite the above equation as such, and then rearrange it to delta G naught equals negative RT ln K. Again, remember here that this is the free energy equilibrium constant. So just like with the Q described above, we're going to be using concentrations for solutions and partial pressures for gases. So think again about what the value of K means for the reaction. If K is very small, the reaction favors the reactants. And if K is very large, the reaction favors the product. This makes sense in terms of the standard free energy change too. If K is very small, that natural log term will be negative. So then delta G naught ends up being positive. And the reverse reaction is spontaneous at standard conditions. And vice versa. When K is large, delta G naught is negative, so the forward reaction is spontaneous under standard conditions. However, just because a certain side is favored under standard conditions, that doesn't necessarily remain true at other pressures, concentrations, or temperatures, which is why we have the full free energy change expression, which includes a Q term. Because if you'll recall, Q can apply to the reaction at any time, not just at equilibrium. In the same way that we walk through different scenarios for different values of K above, we can also look at different Q values, specifically in relation to K. So if Q is greater than K, that means that the RT ln Q term will be greater than the magnitude of the delta G naught term. And thus, delta G as a whole will be positive, which means the reverse reaction is favored. This makes sense because we know already that when Q is greater than K, the reaction has too much product and too little reactant, so it should move towards the reactant. And as is usually the case, the opposite is true for when Q is less than K. So I won't go through the whole example, but you can see here that if Q is less than K, then the products are now favored. Another point I want to hit in this video is something I've alluded to before. When we're given or are calculating the equilibrium constant for a reaction, that K value is specific for that temperature. So if we are given equilibrium concentrations at 298 Kelvin, we can't apply the same ratio of products to reactants for a system at 350 Kelvin. We know from Le Chatelier's principle that if the reaction is exothermic, as in delta H is less than 0, and we add heat, which is kind of like increasing the temperature, the reaction is pushed toward the reactants. This implies then that the equilibrium constant is actually changing, rather than the actual amounts of chemicals changing, though Le Chatelier's principle alone does not quantify this. A way to prove this and determine a new equilibrium constant at a different temperature is with the Van Hoff equation, which I have drawn out here. Now here, K1 and K2 are equilibrium constants at temperatures T1 and T2 respectively. Delta H naught is the standard enthalpy change, and R is the gas constant. This equation is derived from the relationship of Gibbs free energy and enthalpy and entropy. Although I won't walk through the whole derivation here, what's important to understand is that from the Van Hoff equation, if we increase the temperature for an exothermic reaction, the equilibrium constant will decrease. If we increase the temperature for an endothermic reaction, the equilibrium constant will increase. And of course, vice versa for when the temperature is decreasing. So a lot of people struggle with the equations that we've covered today, because there are a lot of easy ways to mess up. Forgetting the negative, using the wrong Q or K, mixing up variables, etc. So don't get too discouraged starting off. There's a lot to keep track of, but I think these equations are tied closely to concepts that we've already gone over. So always be sure to check your understanding and make sure that whatever value you're calculating makes sense with what you already know conceptually.